Hey, everybody, how is it going today? All right. So what we're going to do is continue on. We have been talking about work and energy. All right. If you remember, work is defined as FD cosine of theta. This is a force that you apply to an object. This is the length of the displacement vector. And this is the angle between the force and the displacement vector. All right, we've done some problems with that already. I want to kind of rewrite this a little bit. We could express this thing here as this is equal to F cosine of theta times D, or we could write it as F times by D cosine theta. What does this represent? Well, if you draw the body here, and you have your force applied to it. Now keep in mind, the work is done by a force, and this could be any force. It could be the force of gravity, it could be the normal force, it could be a force that you apply to an object, okay? And we're just going to talk about this one as just some force being applied to the object. Well, I can write this in terms of I can break this in terms of two components. Let's suppose that the block slides in this direction. Then I could write this and say, well, I can replace this force with its two components. This one, this one. So, and I could probably start it here. So it's like there's a force pushing along here by this amount, this green arrow here, and there's a force pushing down. All right. So what is this equal to? Well, if this is theta, here, this is F cosine of theta, and this is F sine of theta. Now this force is pushing down perpendicular to the displacement, and therefore it does not do any work on the body. Why? The angle between this F sine theta and the displacement is 90 degrees, and the cosine of 90 is 0. Do not forget that. A force that is applied perpendicular to the displacement doesn't do any work. Burn that into your brain. This one does. And in fact, this force is parallel to this one. So the work done by this force is just this amount times D. And therefore, it's F cosine theta times it by the displacement. So this equation makes perfect sense in that regard. Okay, just wanted to show you that. Oh, I also wanted to do something else and show you, suppose that I plot this F, and I'll call this F parallel. That's this amount, the force that's parallel to the displacement. And I plot it as a function of displacement. If this force that's parallel, in this case it would be the F cosine theta, whatever force it is, if it's constant, that means that as the object sweeps out this distance D, this force will make a straight horizontal line. So let's say that this is the final. It starts at 0, and this force is applied on the body all the way through D final. What's this F parallel times D? It's the area under the curve. So the work is the area under the force versus the displacement curve. So if I give you a problem where I plot the force as a function of displacement and it looks like this, and I want you to find the work done, all I have to do is find the amount of area under this curve, and that area is equal to the work. Now, how do you find this area? Well, you might have to chop it up in little pieces. There are lots of techniques for doing that. Here, it's just a rectangle. The area is just the distance, base times the height. All right. So those are some loose ends. Kind of tighten up a little bit. Now, we are now going to talk about the relationship between work and energy. Now, I know I told you that energy is the ability to do work. But if you do a certain amount of work on a body, can you tell what happens to its energy as a result of that? And I mean mathematically. This is just an abstraction. Is there a mathematical relationship between doing work on a body and changing its energy? And the answer is yes. And this is called, these equations are called the work energy theorems. And this is going to be a major focus over the next few days. Okay, so we do tie work and energy together. All right, so first of all, let's go and review what energy we're talking about. We talked about two types. We have kinetic, which is due to motion, and that was kinetic energy was 1/2 mv squared. We have potential energy, which is due to location. If the location is due to a gravitational field, then we have that the potential energy due to gravity is mgh. And you may be wondering, well, are there any other kinds of forces that can produce energy? And the answer is yes. So there's a really common one, and that is the spring potential. So the spring potential energy, and I'm just going to go ahead and write down the equation, but then I'm going to show you what this is all about, because we haven't talked about springs yet. All right, and now I think it's a good time to introduce them. Okay, so here we go. Okay, where did I set it down? Don't want it. Now let me hit the pause for a moment. Okay, it was right in front of me. I just didn't see it. So here's a typical example of a spring, okay? And we're going to be dealing with what we call ideal springs. And these ideal springs are such that when they oscillate, there's no loss of energy at the outside. We'll be more careful about defining that a little bit later. And as you'll notice here, as I pull this thing down, if I let go, what happens? It shoots up. Okay, so if I had my nail, oops. If I had my nail down here, let's say if I put it up like this and I let go, this mass could rise up and hit the nail and drive it through the cup. In other words, as I let go, this object will rise up with velocity, and if it hits a nail, it can drive that nail through a cup, apply a force through a distance, in other words, do work on it. The same thing, if I push up on it, and I have my nail down here, when I let go, it could come down, hit my nail, driving it through a distance, and therefore doing work on it. So in other words, the spring itself if you stretch it or compress it, allows you to do work on a body once you release it. Therefore, stretching this spring provides potential energy to the system, stored energy, ready to be released if I let go. And the same thing is if I push it up. If I push it up, again, once I let go, I can tell I must have stored energy in the system, because when I let go, the system starts to move and therefore able to do work. Okay, so it's not just gravity that can store energy. The spring itself can store energy as well. And again, this is called spring potential energy. Now, to understand spring potential energy, we have to understand the force that's caused by the spring. All right, we've talked about forces like friction, normal force, gravity, the applied force, for example, tension. Did I mention tension yet? At any rate, we're going to now introduce another force, and I'll explain here why we haven't talked about this one before. Okay, so I'm going to draw a very simplified view. I like to draw this, by the way, going sideways. That way I don't have to worry about gravity. The gravity's there, but it's perpendicular to motion. You don't have to worry about it too much. So I have here a wall. And I have attached to, resting on the floor is this mass, M. It'd be a block of wood or whatever, okay? And we're going to ignore friction. So this is a very slick floor. We don't have to worry about friction here. We'll introduce friction later as a complicating factor. And attached to this mass is a spring. Now the spring here, this mass is just sitting here. It's not wanting to move left or right. It's in its natural position, okay? What we could also call a relaxed position. And therefore, this is we define as X naught, and this is the equilibrium point. So in other words, we could walk up and we can look at this and see, oh, this mass is not oscillating, it's motionless. The spring is not pushing it or pulling it, it's in its natural state. This point where it's located is called the equilibrium point. Okay. What I'm going to do is I'm going to pull on this mass away, stretching the spring. Okay, so let me draw. Take this part out. I'm going to draw the same system right below it. And this is X naught. But now I've pulled on this mass and I've stretched the spring. Okay, so I've pulled on this mass and I've stretched the spring. And the question is what does the spring do? Well, the spring applies a force to it. The spring is trying to pull that mass back. So that pull is a force. Now, if I'm applying with the same force in the other direction, the mass won't move or won't accelerate. Be careful. So I can pull this thing back and hold it. The mass is not accelerating. But that doesn't mean the spring isn't applying a force. The spring is applying a force. It's just offsetting the force that I am pulling on. Okay, so there is a force now, and it's trying to pull the spring towards me, towards the left. So this is called the spring force. It's also called the Hooke's force. We'll hear about that a little bit later. That's the spring force. There's also names like the elastic force. There's lots of different names for this, okay? And now the question is, well, let's see here. Whenever we introduce a new force, we always have to talk about two things. What direction does the force point and how big is it? Well, The directions here is obvious. If we're pushing it, if you pull this mass away from X naught, this force tries to pull it back to X naught. And therefore, this is called a restoring force. I'll write that down. A restoring force is any force that tries to return an object back to a certain point location, right? Now, how big is it? Well, it turns out that the amount of the spring force is given as Kx, where X is this distance of stretch. This is also written as K delta X, where we just simply denote delta X as the stretch distance, a change in X. Now in your book, and just about everywhere on the planet, they'll put a negative sign in here. No, this equation tells you the magnitude of the force. The direction is denoted by the diagram. So I realize there's a negative sign in your book. I do not agree with it. Okay, just telling you. Now, what happens though if I push in the other direction? Okay, well, let's see here. I'm going to, I guess I could draw it down below. Okay, so I'm going to draw the same system. I have my X naught. And now I'm compressing the spring by pushing the mass in this direction. So now I have my mass over here. And now my spring is highly compressed. Now what? Well, the spring is now trying to push the mass back to X naught. Again, it's a restoring force. And so my force is now directed in this direction. How big is it? It's the same equation. This is, again, delta X. So in other words, if I pull on the spring by a centimeter or I compress it by a centimeter, the amount of force provided by the spring is the same, which is really nice. It's really good that we don't have to have separate force equations for stretching versus compressing. They're the same. Okay, so we could do some simple force spring problems here. Just, get acquainted with it. Go ahead and erase this. Oh, I should mention, you may think, what's K? What's K? I forgot to mention that. K is the stiffness of the spring. It's called the spring constant, sometimes called the Hooke's constant. But it tells you how stiff the spring is. Okay, so if you look at this equation here, if K is really, really large, then it takes a large force to stretch the spring by a certain amount. Therefore, the larger K is, the stiffer the spring is. So the little springs that you take out of your pins, those little things, the K value is very, very small. A car spring, the K value is very large. Okay, so you can think of K as the stiffness factor. All right, so let's see here. So I'm going to hang from the ceiling a spring that has a stiffness factor of 200. Now, what are the units of this? Well, let's go back. F spring is K delta X. This is in meters. This is in newtons. Therefore, K must be in newtons per meter. So a K value of 1 says that the spring requires 1 newton. Let's go ahead and write that down. K is equal to 1 means that it takes 1 newton to stretch the spring by 1 meter. That is a very weak spring. So you think about it, a meter is what? This length here. And a newton is what? An apple. So if I have this spring here and I put an apple on here, it's going to stretch the spring 1 meter. So that's not a very stiff spring. So a K value of 1 is pretty low. That's really, really weak. Okay, but this K is 200 newtons per meter. All right. And so now the question is, what if I place on here? It's just hanging here. So this is X naught. The natural length of the spring, equilibrium point. And then I stick on here an 8 kilogram bowling ball. That's about what a bowling ball is, about 8 kilograms. What will happen to the spring? Well, it'll stretch, won't it? This bowling ball will stretch the spring. So this is the before picture. I'll take the bowling ball out. And then after, this is 8 kilograms. And what is this? This is delta X. It's the stretch distance. Now, what are the forces that act on my bowling ball? I have the force of gravity going down, G, and I have the force of the spring acting up. However, I'm going to let this thing just kind of, I'm going to put the bowling ball in there and just kind of lower it down, let go. I mean, it just let it go. It's going to stay right here. Now, if I just took the bowling ball, let go, it's going to bounce up and down. I'm not doing that. I'm actually just going to lower the bowling ball down until the spring doesn't want to stretch anymore. Then, at this point, this bowling ball is at rest and it's not changing its motion. It's not accelerating. Therefore, the forces acting on the bowling ball must vector cancel. For F spring minus mg is equal to 0. But the force of the spring is positive K delta X minus mg. But if I put the mg on this side, I'll get equal to mg. And I get delta X is equal to mg, which is around 80, divided by K. Yeah, it's about 2.5 maybe meters. So what happens is that this bowling ball will stretch the spring by a total of about 2.5 meters. All right, so there's a typical example of how the spring works. Now you may be wondering, like, well, why didn't you introduce the spring before? You talked about tension and gravity and normal force. Why not the spring? Does anybody know? Why didn't I introduce this force of the spring earlier? Think about that. Well, the reason why is when we go back to our little diagram we did for the Newton, the cause effect thing, right? And so we had acceleration, and we had Newton's second law, and then we had the equations of motion. And when we had cause effect problems, this is how we solved them. We had to find the acceleration, and we ended up either going in this direction with the thing or in this direction. However, when we did this, the equations of motion we used were at that time written for constant linear acceleration. And so this equation, d is equal to, b is equal to, these govern the motion of a body when it's under constant linear acceleration. F, the spring, equal to k delta x. Let's ask, I have it here. The question is, does this produce constant linear acceleration? Well, here we are. Oops. Okay. Now, you know what? Let me get you the other demo. It'll be even clearer this time. Okay. Here's a body that has two springs acting on it. There's this spring and this one. Okay. Now we have gravity acting down, the normal force acting up. They offset each other here. They cancel, they vector cancel. So all we have to worry about are the springs. And the question is that what kind of acceleration do these springs produce? Well, let's go ahead and rocket it back and forth. Now keep in mind, we have to use two springs on this demo because our springs are not really good at moving things in two directions. They're good at pulling, they're not very good at pushing. So we have to use one on each side, but ultimately it's the same. And so what we have here is an acceleration, don't we? This object's motion is not constant. All right, now the question is, well, okay, it is accelerating. Is the acceleration constant and linear? And I would suggest that you turn off your, hit the pause and think about this a little bit. Is this constant linear acceleration? Click the pause. Just do it. I know you don't want to do it, but do it. All right, we're back. Now, to be constant linear, the acceleration has to stay the same value and it has to always point in the same direction, right? The acceleration is a vector, and for a vector to be constant, it must always point in the same direction and it must have the same length at all times. This is the case here. The answer is no. Okay, so let's take a look at here. When this thing is right now doing this, so when it's going in this direction, notice that it starts off with no speed and it gains speed. That means that its acceleration and its velocity must be in the same direction. Remember, when an object is speeding up, its acceleration and velocity vector point in the same direction. Well, its velocity vector is going in this direction. Therefore, it must be accelerating in this direction. So it accelerates initially in this direction. But once it gets past the equilibrium point, and by the way, right there is the equilibrium point. Once it gets past the equilibrium point, it starts to slow down. Okay, but it's still going in that direction. So it's going in this direction here. So the velocity vector is pointing in this direction, but it's slowing down, which means the acceleration vector must point in what? Opposite direction. This direction. So its acceleration vector is pointing in this direction, And now, once it goes back to the equilibrium point, it points in the opposite direction. The acceleration cannot be constant because the direction changes. Furthermore, what's its acceleration through the equilibrium point? Well, at the equilibrium point, you can see this force of this spring must be equal to the force of this spring. It's not accelerating. These forces therefore cancel, so as the object passes through the equilibrium point, its acceleration goes to zero. So when you first let go, the acceleration is at a maximum in that direction, but it gets weaker and weaker and weaker to where it goes to zero in the equilibrium point and then reverses direction, getting larger and larger and larger. That's how the acceleration is working back and forth. So the acceleration changes direction. It also changes magnitude. It goes from a maximum to zero and then to a maximum to zero. Okay, so the acceleration is not constant, not linear. That's why I didn't bring up this force before. It's because it is not one that you want to use these equations on. These equations will not work for objects that have springs attached to them. And in fact, later in the semester, we'll have to derive the acceleration for this particular type of problem. Okay, but we can treat it with energy really easily. Okay, so far, just to summarize, we've got a new force in town, the spring force. It is a, it has this equation where the delta x is either the stretch distance or the compression distance. It doesn't make any difference which one, the equation is the same. Okay, also, this force tends to produce non-constant accelerations, which means that you cannot use these equations of motion. This thing here still works. It's just that these equations that we've used with it cannot be used. We'll have to come up with different equations later in the semester. Okay. Now, I think we are ready. Oh, I should mention. Oh, no, let's wait till. Okay, so let's go ahead and talk now about the work energy theorems. And again, the problem that we have is we have this concept of work. We have an equation that tells us how much work is done if you know the force and the displacement, right? But we don't have any connection between the work and the energy. Well, we do now, because I'm going to write down the work energy theorems. I'm going to write them down. Do not panic. I'm going to explain them here in a moment. They're not that bad. Okay. So I'm going to write it down as this looks okay. I don't know what that C is yet. I'll explain in a moment, but this looks like the definition of work, which it is. This, and now I'm going to put in here this one, which looks identical. And you might think, oh, I know what's going to be on the right-hand side. It's going to be the negative delta KE, right? It's not going to be even positive delta KE. Delta E. And now, these are the two work energy theorems. You're going to have to get to know them very well. I'm now going to start to explain them. So the first thing I'm going to explain is what we mean by E. Well, that one's actually simple. E is the total energy of the system. It's simply equal to the amount of potential energy in the system plus the amount of kinetic energy. The body can have potential energy, and if it's moving, also has kinetic energy. You add those both together, and you get the total energy. Notice this is not a vector equation. And so whatever potential energy in joules you have, let's say it's 4 joules, and this was 2 joules, the total energy is 6 joules. Really easy. Okay. What is this? This negative sign means drop. So this is a drop in the potential energy. But what's the C and the NC? That's the part that's going to take a little explaining. Okay. I will tell you right now that C stands for conservative, and I'm not talking about politics here. And NC, you're thinking equilibrial, right? No, it means non-conservative. It turns out that the forces that are applied to a body can be conservative or non-conservative. And these are the same forces we've always been talking about, tension and normal force and all those things. But those forces themselves can be classified into these two categories. Now, you might think, oh no, how am I going to do that? Well, for physics 2A, it's really simple. Conservative is gravity and spring. Now you know why I wanted to talk about the spring force. And the non-conservative is what? Everything else. So what is actually the definition of these things? Essentially, if a force, a conservative force, does no work if the object returns back to its original location. Or another way of saying it, that the amount of work that's done by a conservative force does not depend on the path that the object takes. It only depends on where the object starts and where it ends. Hang on, I'll explain here in a moment. A non-conservative force is path dependent. If it does depend on which path an object takes from one place to another, now that we explain. All right, so I want to describe the difference between a conservative and a non-conservative force, and it depends on the work they do. Okay, so now here I'm going to do a typical conservative force is gravity. And so I have an object here. Got a circular mass. And what I'm going to do is I'm going to place it on the table at this point right here. So I'm only going to be concerned about the work done by gravity, okay? Not by my force, gravity. So what I'm going to first do is I'm going to lift my mass up and push it over here and put it to its final location. Now, how much work is done by gravity? Well, it's only going to be dependent on what? The fact that it started here and ended up there. Suppose instead I had slid this object over this direction, lifted it, and brought it here. Let's suppose that this path here requires an amount of work done by gravity equal to W1, and this is W2. Let's suppose instead I lift the object up way high, I bring it over, and I lower it down to here. This is the amount of work done by gravity we'll call W3. How much work is done in all these three paths? The same amount. By gravity. Gravity does the same amount of work regardless of which path I take, because the work done by gravity only cares about where you start and where you finish. In this case here, the work done by gravity being path independent, it means that the force of gravity is a conservative force. Now, the same thing would apply with the spring. Okay, so for example, here is my spring, and I place a body on here. When I pull it down, and I release it. What does this body do? It goes wing, 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 like that. Okay. Well, how much work is done by the spring if the object starts at this point and ends at this point? In other words, I let go, the object rises to here. And the spring does work on the body. Why? Because it's applying a force through a displacement. And it turns out that the amount of work done by the spring force as it rises from here to here doesn't matter how many times it oscillates. Because the amount of work done by the spring only cares that it started here and ended here. Regardless if it did it 8 times or 1,000,000 or whatever, it makes no difference. The amount of work done by the spring is independent of the path. It only depends on the starting and ending points. So the work done by a spring is conservative. And this is where we end up introducing the term ideal spring. What I've just described is true for ideal springs. A non-ideal spring, which is kind of a bad spring, doesn't quite follow this. And so we have an idealized concept of the spring where this is true. So all you have to remember is that the spring force and the gravity force are the only conservative forces. Now, when you take physics 2B, we'll introduce a couple more, okay? But right now, it's just those two. Now, what about a non-conservative force? I'll show you. The most obvious non-conservative force, although that's really not strictly true, but the most obvious one is friction. So now I'm going to take a bird's eye view. I have a brick resting on a surface that's rough. And I'm going to push it from here to this point. So what I do is I come along here and I'm going to ask about the work done by friction. Okay, so I'm going to come along here and I'm going to push like this object along this path, and it's going to end up at this point here. Now, as I'm pushing, friction is doing what? Pushing in the opposite direction. So as I'm pushing this thing, friction points in this direction. Notice that the work done by friction is negative. The displacement is in this direction. The force is in the opposite direction. Friction's losing. Friction wants to make the object go in this direction, but the object is going in the opposite direction. Okay, so the force of friction is negative here, but that's not what we're interested in. The amount of work done by friction, in this case, we can write down as W1. But then I come along later and decide I want to do it differently. I'm going to push this box first along here, then I'll do it here. Now, as the box travels along here, here's an intermediate spot, the force of friction does what? It acts in the opposite direction. And you'll notice, again, the displacement in this is in this direction. Force of friction is the opposite. This is negative work. But it's not whether this work is negative or positive that matters. The amount of work done here on this path, W2, is going to be greater than W1. You can tell because you're going to be a little bit more tired pushing it along this path than this one. And therefore, the amount of work done by friction is different for these two paths, means that friction is a non-conservative force. What other non-conservative forces are there? My pushing. I'm applying a force to the brick, right? So here I am pushing on the brick. We'll call that F of me. My force is non-conservative. The force that is acted upon by the normal force, non-conservative. Okay, I would point out a board here. Now notice something though. The work done, I should say, the force of gravity is non-conservative, but it doesn't do any work. Okay, so it is possible that a force, again, acts on a body, doesn't do any work. So yeah, normal force, non-conservative. Friction, really common, non-conservative. And like tension force is also non-conservative. Pretty much everything but gravity and the spring force are going to be non-conservative. Okay, that's enough for the day. Tomorrow, I'm going to show you how to use these work energy theorems to solve problems really easy that you can't do doing Newton's second law.